Hello and welcome to the A-level lecture series. In this section, video, we're going to look at section 2 of chapter 19. So we're going to look at two new enthalpy changes that we had not yet discussed. The first being the enthalpy change of atomization and the second the electron affinity. We need to discuss this in order to talk about lattice energy because both of these two enthalpy changes, along with some of the ones from chapter 6, are going to affect the Hess cycles that we form for the lattice energy. So before we talk about the overall math and Hess cycles for lattice energy, we need to discuss what atomization and electron affinity are and how we can incorporate them later on, as well as their trends and whatnot. So let's get started. So let's first talk about atomization, which I think is the easier of the two. The standard enthalpy change of atomization, or delta H standard AT, is related to the conversion of an element in its elemental form to the gaseous atomic form. Now, this is very specific, gaseous atomic form, not molecular, meaning that we're turning this from elements from whatever initial state they're in to a single atom in the gaseous form. So what is the official definition for standard enthalpy change of atomization? The enthalpy change, and again, we're always going to have that enthalpy change component because we are defining enthalpy changes. When 1 mole of a gaseous atom, so here the 1 mole is of the gaseous atom, so this is a product here, is formed from its elements under standard conditions. So this means the element in its natural form, its elemental form. So if we're talking about hydrogen, we'll be talking about H2 gas. If we're talking about bromine, it will be Br2 liquid. If we're talking about sodium, it will be Na solid. So we're going from the element in its elemental form, its standard form, to 1 mole of a gaseous atom of that same element. Those are the two key components of atomization. Now, the value for enthalpy change of atomization is always going to be positive. This is always an endothermic process. Remember that if an enthalpy change is positive, that means that it's endothermic. So atomization is always endothermic. It always takes energy to go from an element to its gaseous atom form, because they're going to have to overcome the forces holding the atoms together, should say plural. Either the bonds, if we're looking at a diatomic element like hydrogen and bromine, or the energy of the intermolecular forces if we're looking to change the state of matter from solid to gas or liquid to gas. So enthalpy changes of atomization we can represent with equations, just like most other enthalpy changes. And these equations are going to look a few different ways because they can do two things. Atomization can involve the changing of the state of matter. So if the element under its standard form, like lithium, for example, is not a gas, atomization says we're turning this to 1 mole of the gaseous atom. So lithium solid, for example, when we're doing the atomization of lithium solid, what we're doing is going from lithium solid, an atom in the solid state, the elemental form of lithium, to lithium gas, an atom in the gaseous state. Because remember, atomization is changing to 1 mole of a gaseous atom. So single atom, just Li, gaseous meaning gas form. So the enthalpy change of atomization of lithium involves just changing the state of matter. But for a diatomic molecule like chlorine, for example, chlorine elemental form is Cl2 gas, we're not changing the state of matter. Chlorine is already in the gas form. However, chlorine is a diatomic molecule. Chlorine consists of 2 chlorine atoms single bonded together. In order for atomization to happen, we need to break that single bond between the chlorine atoms. So how do we do that? We need to overcome the bond energy between the chlorine atoms. So chlorine involves not the change of state of matter, it involves the breaking of bonds, also an endothermic process. So we're going here from Cl2 gas to Cl gas. Now, something that you have to be aware of is that, again, we have 1 mole of the gaseous atom being created in the enthalpy change of atomization. So when we write these equations, this Cl gas has to be a 1, meaning that because chlorine is diatomic, we actually need a 1/2 in front of our Cl2 gas, because we're only creating 1 atom in the gas state, not 2. Now, for some elements, we're going to need to do both of these, both change the state of matter and break the bonds. An example of these will be bromine. Bromine in its elemental form is a liquid element. So we need to change the state of matter from liquid to gas, which involves overcoming the London dispersion forces that are present in bromine. But also bromine is diatomic, meaning that we need to break the bromine-bromine bond in the molecule. So when we write the equation for the enthalpy change of atomization of bromine, we are actually looking at an endothermic process because it involves both breaking the bonds and changing the state of matter. Now, again, do notice that some of these will require us to have fractions as coefficients, depending on whether or not that element is diatomic in its elemental form, because these atoms in the gas state that we have as the products are always going to have to be a 1 because of the definition. So this is why these are all endothermic. The enthalpy changes of atomization are all endothermic because we're either breaking the bonds that are formed in the molecule, which is an endothermic process, bond breaking. And these are covalent bonds that we're breaking. Or it's going to be an endothermic process, because if we change the state of matter, that's also endothermic, because we're going always towards gases, meaning that we're breaking intermolecular forces. More specifically, because these are elements that are going to be diatomic single element molecules, we're breaking the London dispersion forces of the molecule. So either here chlorine or actually not in chlorine because it's already a gas, but in bromine we'll go from liquid to gas. If we are looking at a metal, so this London dispersion forces if it's non-metal. If we're looking at a metal, we're breaking metallic bonds. So we're looking at a metal, we're looking at breaking metallic bonds instead of intermolecular forces. So it's breaking intermolecular forces for non-metals, which are going to have London dispersion forces, or in the case of a metal like lithium, we're breaking the metallic bond in that metal lattice, right? So that's the standard enthalpy change of atomization. Next, let's look at electron affinity, which is the other enthalpy change we have to look at. And this one's a little more complex and have a little more steps. But in reality, what electron affinity is the polar opposite of ionization energy. Remember that ionization energy is the amount of energy needed to create a cation, a +1 cation. So let's really briefly go over that again. So ionization energy, I'm going to put this in yellow. Which we learned about in AICE chemistry, is the enthalpy change when one mole of electrons are removed, from 1 mole of atoms in the gas state to form actually, we're going to leave that to form 1 mole of atoms in the gas state. Now, we could say to form a 1 mole of plus 1 ions, but that's only if it's a first ionization energy. If you recall, we can have first, second, third ionization energy. So the enthalpy change when 1 mole of electrons are removed from 1 mole of atoms in the gas state. Now, when we talk about ionization energy, we are essentially talking about the creation of cations. We're talking about going from the gaseous atom, so an atom of an element in the gas state, to an ion, positive ion, of an element in the gas state. So, creation of cations by the removal of electrons, right? So that could mean if we're talking about the first ionization energy, so we'll say first ionization energy of sodium, for example, will look like this. Na gas yields Na plus an electron. If we're talking about the second ionization energy of sodium, we're talking about going from Na plus gas, because once we're to the second ionization energy, 1 electron has already been removed, to Na2 plus in the gas state plus an electron. So on and so forth. If we're talking about the third one, which will be the last one I do, we're talking about going from Na2 plus gas to removing the third electron to create Na3 plus gas plus an electron. So that's the ionization energy that we learned in AS chemistry. How is this related to electron affinity? This is the exact opposite of electron affinity. In this process, we're removing electrons to create positive ions. Electron affinity deals with adding electrons to create negative ions. The electron affinity is related to the creation of anions by gaseous atoms. And again, we're working in the gas state as well, so we need to keep that in mind. The first electron affinity, because just like with ionization energy, you can have first, second, or third, etc., etc. The first electron affinity is the enthalpy change when 1 mole of electrons, and it's always, remember, things are done in 1 mole at a time, 1 mole of electrons is added to 1 mole of gaseous atoms to form 1 mole of gaseous ions with a single negative charge under standard conditions. So again, because we're looking at the first electron affinity, we are removing let me make this bigger. We're removing 1 mole of electrons. Sorry, we're adding 1 mole of electrons is added. So the exact opposite of ionization energy. In ionization energy, we remove 1 mole of electrons. In electron affinity, we add 1 mole of electrons to 1 mole again of gaseous atoms, meaning each atom gets 1 electron, to form 1 mole of gaseous ions with a single negative charge. Now this, with a single negative charge, I'm actually going to put in a different color. So with a single negative charge. Why is this important? This part, the single negative charge, is only because we're looking at the first ionization energy, electron affinity. If this was the second electron affinity, then it will have a -2 charge. Third electron affinity will be the -3 charge, so on and so forth. But the parts in blue always stay because they're part of the definition of electron affinity. 1 mole of electrons added to 1 mole of gaseous atoms or ions, if it's second or third, to form 1 mole of gaseous ions. Now, what charge those ions will have, it will depend on which ionization, electron affinity we're looking at. So, electron affinity is sequential, just like ionization energy. So, many electrons can be removed. If we wanted to look at the second electron affinity, the second electron affinity would just be the enthalpy change when 1 mole of electrons is added to 1 mole of gaseous -1 ions to form 1 mole of gaseous ions with a -2 charge under standard conditions. So definitions are very similar, but what changes is the charge of the final ions and whether we're adding these to atoms or an ion with already a charge. You have to keep this in mind. When you think of these definitions, don't just memorize the definition, look at which sequence it is, first, second, third, and then you can adapt the definition slightly. The base definition is still the same. 1 mole of electrons added to 1 mole of either atoms or ions to form 1 mole of ions, and then the charge of those ions will depend on which electron affinity we're looking at. So let's look at the electron affinities for oxygens to look at a clear picture, the first and the second. The first electron affinity of oxygen, which is negative 141 kilojoules per mole, will be if we were to grab oxygen gas at the atom, not the ion, because it's the first electron affinity, add 1 mole of electrons to 1 mole of those oxygen gas atoms, and create 1 mole of O minus gas. So unlike ionization energy, where the product was positive, with electron affinity, the product is going to be negative. If we wanted to look at the second electron affinity of oxygen, we will then start with this O minus ion. The second electron affinity starts where the first one ends, with that O minus gas. Then again, the process is the same. We're just adding 1 electron to that O minus gas, and we're making its charge essentially go down 1, so O2 minus gas. That second electron affinity for oxygen is positive, 798 kilojoules per mole. Now notice that in order to figure out how much energy is required to go from neutral oxygen to O2 minus ions for 1 mole of ions, we have to actually add both of these electron affinities. The electron affinity is just for the addition of the 1 electron. Meaning that when we look at these numbers, negative 141 is how much energy is released by adding the first electron, whereas 798 is how much energy it takes to add the second electron. So if we wanted to know how much energy it takes to go from O gas, add 2 moles of electrons to that to make O2 minus gas, which is essentially the addition of both of these. And actually, let me write it right below it. So if we add these two together, we'll have O gas. The O minus gas cancels out, plus 2 electrons, yields O2 minus gas. If I wanted to figure out how much energy this took, I will have to add both of these electrons affinity, the first and the second, which would give me, let me do some quick math here, around 657 kilojoules per mole positive. So the enthalpy change required for both of these steps to happen is the addition of the enthalpy change of electron affinity for the first and the second electron affinity. All right. So keep that in mind. The second electron affinity does not mean the amount of energy needed to remove 2 electrons. It's just the amount of energy needed to remove the second, to add, not remove, to add the second electron. So if we wanted to know how much energy it takes to add 2 electrons, we have to add both of these electron affinities. Now let's talk about the trend in electron affinity. Electron affinity does not have a predictable trend like ionization energy did. There are a few trends that we can outline with electron affinity, but it's going to be a lot less stable and a lot less trustworthy, essentially, than what we saw for ionization energy. In general, the first electron affinity for an element is going to be negative, but there are exceptions to this. There are elements with positive first ionization energy, electron affinities. I don't see any here, although here we can see nitrogen actually it's around 0 or plus or minus 19, and that's just because of uncertainty. But in general, the first ionization electron affinity for an element will be negative, and the electron affinities after the first one will always be positive. So the first one, usually negative, there are some exceptions. Second electron affinity and up, always positive. The reason behind this is fairly simple. It's going to take energy to add to add an electron to something that's already negative. Remember, when we do the first electron affinity, we are going from something that is neutral, so we'll just neutral, to a -1 charge. When we do the second electron affinity, we're going from something that is -1 to -2. Third electron affinity is something that is a -2 to -3. So on and so forth. So what happens? In the first electron affinity, we are adding an electron to something that is neutral in charge, meaning there is no repulsion there. But once we get to the second electron affinity and on, we're adding an electron to something that already has a -1 charge, or an electron to something that has a -2 charge, meaning that these two, or anything after the first one really, is going to experience repulsion. In order to overcome repulsion, we are going to need energy. So that enthalpy change is going to be positive. Whereas because the first electron affinity doesn't have experienced repulsion, we are not necessarily going to get that positive enthalpy change. We'll usually get a -1, although sometimes it is still positive. Now, general electron affinity for non-metal atoms like chlorine, fluorine, bromine, etc., that you see here, is going to be more negative or more exothermic across a period with a maximum of group 17. So we can see that here. If we go across this first period right here, -122, 0, -141, -328. If we ignore the nitrogen, which has its own unique challenges, we can see that it's getting more and more negative. If we look at sulfur and chlorine, which are in the same group, -200 to -348, more negative. Selenium to bromine, -195 to -324, more negative. So generally speaking, and again we say generally because things like nitrogen, non-metal atoms are going to get more negative or more exothermic in electron affinity as we go across the period from left to right. And finally, only group 16 and 17 elements have a pattern for electron affinity down the group. The electron affinity gets less negative or less exothermic as you go down the group, excluding the first element. So as you can see, we go -141 to 200. So excluding the first jump, then it goes down. 200 to -195 to -190. Again, if we exclude the first jump from 328 to 348, then it starts going down from 348 to 324 to -295. So these are the trends in electron affinity. You have to take them with a grain of salt. They are not as predictable as the trends in things like ionization energy or atomic size, but they can help you, and you might be asked about them. Now finally, what factors affect electron affinity? Out of all of the conversations we had in this section, this should be the easiest. Why? Factors affecting electron affinity are going to be the exact same factors that affect ionization energy, atomic size, ionic size, which are the three basic factors that affect every atom: shielding, size, and nuclear charge. Electron affinity is going to be mainly influenced by whatever influences the attraction of the incoming electrons for the nucleus of the atom. As we talked about in chapters, I think it was chapter 2 or 3 or 4, as well as many other times, like in chapter 10, the more electrons are attracted to a nucleus, the more exothermic an enthalpy change will be that's related to it. The electron affinity will be more negative, more exothermic, the more these incoming electrons are attracted to the nucleus. So what makes these electrons more attracted to the nucleus? Well, the same things we talked about a million times. The larger the nuclear charge, the larger the number of protons in an atom, the more energy will be released by the electron affinity, the more negative or exothermic the electron affinity will be, because the electron that is added has a stronger attraction to the nucleus. The farther away the outer shell is from the nucleus, meaning the more energy levels that atom has, the larger the atom, the less energy will be released. Why? The larger the atom, the farther away the nucleus is from the incoming electron, and so it has a very weak attraction for the nucleus. And finally, very, very hand to hand with what we just talked about with size, the more energy levels an atom has, meaning the more shielding an atom has, less energy will be released when the electron is added because, again, the shielding causes a weaker attraction to the nucleus. So we can view this and we can talk about these factors that affect electron affinity, just like we talked about the factors that affected ionization energy and atomic size. It's just going to be a matter of the number of protons, the size of the atom, and the number of energy levels or shielding. So when you're talking about this, just think to yourself, how do these factors affect the attraction of the incoming electron to the nucleus? The larger nuclear charge, more protons, means more attraction, which means more energy release, more exothermic. The farther away the incoming electron is, meaning the larger the size of the atom, the less energy is going to be released because there's a weaker attraction for the incoming electron to the nucleus. And the more shielding that atom has, less energy is released again because that shielding is going to cause a weaker attraction. Weaker attraction means less energy released. All right? So those are the factors affecting electron affinity that are exactly the same as the factors affecting ionization energy. That is it for section 2 of this chapter. I will see you all in the next video to start talking about the most complex part of this chapter, which is going to be the Hess cycles.